I decided to look at the paper by Piech and their colleagues. And one way to understand deep knowledge tracing is to start with what doesn't work anymore. I think before this paper, a lot of models in STEM education treated student performance as something you could explain using snapshots. You look at things that were recently correct, maybe some summary of features, and try to predict what comes next. That works up to a point, but it breaks down once learning becomes more complex and more sequential. That's the gap this paper is responding to. The authors argue that if learning unfolds over time, then the model has to unfold over time too. That's why they moved to recurrent neural networks instead of non sequential models like SVMs. RNNs aren't just a different classifier here, they represent a different way of thinking about the data. Rather than asking, what features explain this response, the model asks, how did we get here? RNNs assume that student learning is history dependent. Every interaction updates an internal state, and that state carries forward. What a student does now is shaped by everything they've done before, not just by the last question or a fixed set of engineered features. That assumption is doing a lot of work in this paper. And it's exactly where feature based models start to struggle. In earlier approaches, if you wanted a model to care about time, you had to manually encode it. You decide which past actions mattered, how far back to look, and how to summarize them. In deep knowledge tracing, the RNN learns those dependencies on its own. The temporal structure isn't designed ahead of time, it's learned. That's where the shift towards representation learning really shows up. The model isn't told what knowledge should look like. Instead, it develops a representation that evolves as the student interacts with the system. Knowledge becomes something continuous and dynamic, not a set of predefined skills with fixed parameters. This gives the model real advantages. It can capture long range dependencies, adapt to different learning paths, and scale well to large STEM datasets. In the paper, the RNN consistently outperforms traditional knowledge tracing models across multiple benchmarks. But those gains come with trade offs. RNNs lead large amounts of data, which makes them less practical in small scale classroom studies, similar to what we looked at last week. And while the model is powerful, it's harder to interpret. You gain flexibility and expressiveness, but you lose some of the transparency that we saw in those previous models. So, what this paper represents isn't just a new technique, it's reframing the problem. Learning is no longer being treated as a static state to be classified, but as a process to be modeled. In this context, deep knowledge tracing marks a clear move away from feature engineered models towards sequence based representation learning. And that shift fundamentally changes what kinds of questions educational AI can ask.